so what we're doing here, this is the second VCast for energy, and we're going to get in depth on kinetic energy. Now, we've already talked about that kinetic energy is energy stored in the motion of an object. And we haven't done the equation yet because we've been working on the conceptual relationship of how potential energy can be turned into kinetic energy. But here's the equation for it. Kinetic energy is just 1/2 times the mass times the velocity squared. Looking at that equation, is kinetic energy more dependent on the mass or the velocity? Well, let's just put in some numbers here to figure this out. Let's go ahead and just put like 1 and 1. All right, so if I just have kinetic energy is 1/2 times 1 squared, that would get me a baseline of 0.5. Now, if I double the mass to 2, now 1/2 times 2 is 1, times 1 squared is 1. So if I double the mass, the kinetic energy doubles. But if I double the velocity instead, all right, 1/2 times 1 is 1/2. Times 2 squared, which is 4. 4 times 1/2 is 2. So you can see that the velocity, all right, has a much bigger effect on it. When I doubled the mass, it only doubled the kinetic energy. But when I doubled the velocity, it actually quadrupled it because it went to the square. All right. So it's much more important when talking about kinetic energy that you're going to be looking at the velocity, all right, as the biggest factor. So let's jump into using that equation first. All right, how much kinetic energy does an 8 kilogram mass traveling at velocity of 5 meters per second have? Okay, well, again, kinetic energy is 1/2 mv squared. I know the mass is 8 kilograms. I know the velocity is 5 meters per second. I can use that equation to come up with 1/2 times 8 kilograms times 5 meters per second squared. And let's see here. So 1/2 times 8 times 5 squared gets me 100 joules of energy. So in this case, kinetic energy is 100 joules. Simple enough, right? Well, let's change this around a bit. How much kinetic energy does a 4 kilogram ball have after being dropped from a 200 meter building? So this is not, again, where we can use that equation, 1/2 mv squared. What we have to remember is that if we are considering these two locations, potential energy, kinetic energy, for example, of a ball up here, it's all potential energy and no kinetic. And by the time that ball gets just above the ground, all right, there's no potential and all kinetic. So it's transferring here. So let's look at this then. This is a review, something we've done before. We know if we can figure out the potential energy you had at the top of this 200 meter building, we can figure out the kinetic energy down here at the bottom. And remember that potential energy, gravitational potential energy at least, is the mass times g times height. I do know the mass is 4 kilograms. G here on Earth is 10 newtons per kilogram. And the displacement, the amount that it's going to fall, all right, is 200. So plug them in. 4 kilograms times 10 newtons per kilogram times the height of the building, 200 meters. All right, so that would get me oops, 4 times 10 times 200, 8,000 joules of energy. All right, so if the potential energy at the top is 8,000 joules of energy, then I know it has 800 joules of kinetic energy at the bottom. Bring this up because how fast is that 4 kilogram ball after being dropped from that 200-meter building? Well, two ways we can solve this. We're going to split it the old way, all right, and the new way. So first off, the new way is going to be the kinetic energy is 8,000 joules. All right, and let's look at the old way though. All right, you actually know how to solve this, or you did back in Unit 2, where we had a couple different equations with acceleration and time and velocity, all right, and displacement. Okay, well, we know the ball is going to fall at negative 200 meters. Oops. Correct? And we know that the acceleration of an object in free fall, okay, assuming no, is negative 10 meters per second squared. All right. And a few things. We know that the time it's going to take 2 times displacement over a. So we know it's going to fall for a certain amount of time, which we need first. So 2 times the negative 200 meters over the negative 10 meters per second squared gets me, let's see here. Oops. The calculator. All right, so 2 times negative 200 times, divided by negative 10, and then the square root of that. There we go. All right, so that's going to be 6.3 seconds. And then we also know that the velocity is acceleration times time, so negative 10 meters per second squared times 6.3 seconds. It's going to be falling at 63 meters per second by the time it hits the ground. Great. So that's the old way, two-step process, works fine. However, we can take that kinetic energy equals 1/2 mv squared and rearrange that to solve for the velocity. Okay, and you're going to kind of notice this looks a little familiar. That 2 times kinetic energy over the mass square root is the velocity. Not too dissimilar format as that. Okay, so velocity, I do know the kinetic energy from the last one is 8,000, 2 times that, joules, over the mass, which was 4 kilograms. All right, so 2 times 8,000 divided by 4, square root, and voila, there you go. Same amount, 63 meters per second. So just a different way of doing it in terms of energy this time. Got one more for you now. All right, so one more problem here. So imagine back when we watched that gravity video, we saw Superman the Ride, where there is a roller coaster that shoots you off at a tremendous speed, in this case, a velocity of 100 miles an hour, which works out to be a velocity of 44.5 meters per second. Okay? And we want to figure out how high that car goes. In other words, we want to find that displacement. Well, a few things that we want to talk about. First off, can't directly solve for this, but in a roundabout way, we can get there. And first, let's talk about the kinds of energy you have in each spot. Down here we have a total amount, of, down here we have all kinetic energy, and then that kinetic energy slowly turns into potential until you reach that highest point. Right. Down here we can solve for the kinetic energy, so let's go ahead and do that. We have 1/2 times an 800 kilogram object times its velocity of 44.5 meters per second squared. So let's see here. That gets a total amount of kinetic energy of 792,100 joules. All right, but we want to know stuff about this location, and that's where this comes in. We know that then we have 792,100 joules of potential energy. Now, potential energy, in this case, it's gravitational, is mass times g times the height. Well, that height is really just this displacement. So, if we rearrange that equation, that the height is equal to the GPE over the mass times g. So, let's go ahead and plug those in. 792,100 joules over 800 kilograms times 10 newtons per kilogram. That gets a height of just about 99 meters. All right, don't forget to do the questions that follow.